Hey guys, so in this video we're actually going to see how some of those rotational kinematics play out in this problem. And the problem is asking how fast must a centrifuge rotate if a particle 8 centimeters from the axis of rotation, that's just the point at which it's revolving around, is to experience an acceleration of 100,000 g's in magnitude. Wow. Now I put magnitude because I just want to make the distinction that we're talking about the scalar part of gravity, not the vector part. The direction isn't what we're looking at when they say 10,000 G's. That's just 10,000 times the magnitude of gravity. And here I've written down some of the analogs where in an initial problem where you would have had V naught, actually I'll go through the problem, then I'll explain these steps. So how fast must the centrifuge rotate? Now we're going to assume that the centrifuge immediately, it starts, think of it, well here's the example, think of it like this. This is your centrifuge, and let's just say you turn it on. This is not practical because it doesn't automatically start at that speed, but let's just assume that this is a very, very efficient centrifuge. When you turn it on, it automatically starts spinning with some acceleration, and it holds that acceleration constant. But in any event, our initial velocity in this case would be 0. So where you would put a V naught representing linear velocity, you're going to put omega naught, which represents initial angular velocity. So this is 0. Now, the second part of it, it says the angular acceleration that it's going to experience. We know that we're dealing with an angular acceleration because it's rotating around a point, an axis. It has an axis of rotation, or it's rotating around a point. So I know that this is what my omega is going to be. My omega is going to be 100,000 times g. Now, the second part of it, it's asking how fast it must rotate. So now we're talking about its angular velocity after a point. So our omega f or omega final, we don't know. So ultimately, this is what they're asking us. How fast must the centrifuge rotate if a particle 8 centimeters from the axis of rotation has to experience an acceleration of 100,000 g's, starting from rest, and given that the acceleration is 100,000 g's, what must the final velocity, or what speed must the centrifuge obtain in order for this to happen? Now, looking at the question initially, you're probably figuring out how you're going to go about this. Well, always remember that you have relationships. Do you remember this equation? Omega is equal to v squared over r. Angular acceleration, well this is a, is equal to v squared over r. And you may want to question, does this relationship hold here? Well, of course the relationship holds, because we're still dealing with rotational motion, and this is constant. So this is going to tell us at a point in time, given a velocity, given a radius, and given an angular acceleration, I can find what I need. If I know angular acceleration, or even more so, if I know the velocity at a point in time and I know the radius at a point in time, I can find the acceleration at a point in time. So what happens now is I don't actually have to go through this. And furthermore, I'm just going to express this relationship, because recall that v squared is actually, v is equal to r omega, because we don't know the linear velocity. This says the linear velocity at some point squared divided by the radius is going to give me the angular acceleration. So what I'm going to do here is I'm going to substitute that. So I have r omega squared divided by r, because I know nothing about the linear speed of this particle at any point in time, but I do need to find out information about its angular velocity at some point in time. So you see that this wasn't even needed here. And that's why it's always good to write out what you have and to talk about the problem, because sometimes the problem becomes a lot simpler than you would have thought, because here I wouldn't have known how far it traveled, I wouldn't have known how long it took, and could I have solved it without those variables? I'm not entirely sure. Do I want to find out? I don't particularly want to, because physics is beautiful in the sense that we like to find the shortest route to the answer, or the most elegant route, and I feel like this is much more elegant than what's happening down here. So expanding this, I end up with r squared omega squared dividing by r. One of my r's cancel out, and you end up with angular acceleration is equal to omega squared r. And you're going to see this a lot more often. This is just the introduction, and it's nice that this was derived in that fashion. So I have angular acceleration is equal to omega squared over r. I want to find omega squared, so omega is equal to alpha r times the square root. I think, oh, see, I made a mistake. I know that looked a little weird. So omega is equal to alpha over r times the square root. And what is alpha? Alpha is 100,000 times g. But g is equal to 9.81 meters per second squared. So we're going to have to plug that in. And what is the radius? The radius is 8 centimeters, and 8 centimeters converted to meters. I'm just going to write that here. 8 centimeters, or 0.08 meters, because there are 100 centimeters in 1 meter. So here, now I just have to solve this. So I have 100,000 times 9.8, and then I'm going to divide that by 0.81. Sorry, 0.81. I'm going to divide that by 0.08. And now I'm going to square root that answer. So square rooting this gives me, and I can't find the square root function on my calculator. There it is. So my final answer is 3,501.78 radians per second. That is how fast the centrifuge is going to have to rotate if a particle 8 centimeters from the axis of rotation is to experience an acceleration of 100,000 times the gravity, the force of gravity, which is very fast. So in other problems, I'm going to take the same approach. I try to solve them on the spot so you can see my thought process when I solve the problem, because immediately I don't know where the problem is going to take me, nor do I know how I'm going to solve it actually. So this was my initial thought process, but then I realized that there are things that I don't have, but I do know this relationship relating the linear velocity to the angular acceleration. And then in the previous video, we know we had the relationship between the linear velocity and the angular velocity. So I use those relationships to form a relationship between angular acceleration and angular velocity.